Okay, today we will talk about warehouse layout optimization. And here you can see our libraries, NumPy, SciPy for optimization, Matplotlib for visualization, and other things. Here for warnings, we'll ignore them. And here some visualization settings, and I will pass. And let's start. Okay, now before we jump into the actual optimization part, look at the top where we defined a few simple data structures. And what are they? You will notice storage location, product, picker trip. These are just containers for information. For example, a product carries its demand frequency and its volume. The storage location has coordinates and a capacity value. Nothing tricky there, but these pieces give us the language we need to describe the warehouse. Okay, I'll continue. We move into the main class, Warehouse Layout Optimizer. This is where all the logic comes together. When you create an optimizer object, you hand it the list of locations and products. Internally, it prepares a few dictionaries so that later we can quickly look up where each product ends up or what information is tied to a location. Okay, now one of the early methods inside this class is here, calculate distance matrix. If you look at that loop, what we are doing is pretty straightforward. For each product and each location, we find how far it is from the nearest IO point. Okay, and we do that by taking the Euclidean distance. That's the classic square root formula and written as like NP high path log x log y minus y. Okay, then we multiply that distance by the product's demand frequency. So if a product is ordered more often, its distance carries more weight. That number becomes the cost we want to push downward in the assignment step. Okay, I am continuing. Right after that, in the optimized assignment method, you will see the line with linear sum assignment. This operation takes the cost matrix we built and tries to pair each product with exactly one location in a way that keeps the total weighted distance as small as possible. You can think of it like, given all these choices, which pairing makes the walking effort smallest overall, and once it finds that pairing, we store those assignments in a dictionary. I hope that is okay. And look at that. Calculate total travel distance just walks through the final assignments again and adds up the weighted distances so we can print it and show how good our solution is. It uses the same Euclidean distance formula I mentioned earlier, but now only for the chosen pairing. Okay, now look at the part called generate picker trips. This is where we simulate the workload for the pickers. For each picker, we plan several small trips, and instead of picking randomly with no pattern, we use demand frequencies of products to control which ones get picked more often. And you will notice the line where NP random choice uses a probability distribution. That distribution makes a product with higher demand frequency more likely to be chosen for a trip. So each picker gets a list of product IDs they are supposed to collect, and for each product we already know the assigned location. That gives us a full list of picking tasks. Okay, now once we know that what each picker needs to collect, the next question is how do they move through the warehouse? The method calculate trip path is answers that. And we start from an I/O point, then for each product on that trip we compute the walking distance again using that same NP high path. Okay, and that formula here you can see. And we divide that distance by the walking speed to estimate how many minutes it takes. So if the distance is d and the speed is s, then the time is distance divided by speed. At each step, we add a small fixed delay of half a minute to represent the picking action. Then, once all items are collected, the picker returns to the I/O point. Okay, I'll continue. The simulation method. Simulate picker paths. Simply runs that path calculation for all trips of all pickers. The result is a nested dictionary where each picker ID has a list of trips and each trip has its time-stamped coordinates. Okay, and now below the class definition, you see that we are actually creating example data, and here we make 20 locations arranged in a grid and then 20 products with random demand frequencies and volumes. These values don't mean anything special, they are just for demonstration. Then we create two I/O points at coordinates, and what are they? 0, 0 and 40, negative 10. Okay, let's continue. Here, once the optimizer finishes assigning products to locations, we start plotting. So let's move down to where the figure is created. We set a few styles so the plot looks clean. Then we begin drawing the storage locations. If you focus on that loop, we determine how big each marker should be depending on the demand of the assigned product. So higher demand products appear as bigger circles. And the actual size formula is here 200 plus demand frequency times 10. Okay, and that is done. So continue. Each location gets a color chosen based on demand to. When a location has an assigned product, we compute how strong the color shading should be by dividing the demand frequency by 50. And that doesn't represent anything specific, it just gives us a smooth gradient. Okay, and look again. So here, other things for plots. We draw the I/O points as large star markers and label them here because these are the key spots where pickers start and their tasks. And you will see the lines connecting I/O points to product locations here. Those represent the final product location assignments. Each line's thickness depends on the demand frequency. The formula for the line width is 1 plus frequency divided 15. And the line transparency also changes with demand so that higher frequency products appear more visible. Okay, that is done. And after that, that first figure, we open another one titled Picker Trip Analytics Dashboard. And what's happening here? Let's look at this. Picker Trip Analytics Dashboard. And this section answers questions like how many trips does each picker have? How many items do they usually pick per trip? When do they leave for each trip? Each subplot shows one of those aspects so you can get a sense of workload distribution. other things, and most frequently picked product for visualizations. And in here, matplotlib is important. You should know that. And here, travel distance by picker, you can see. And here, summary metrics parts, and I will pass. You know what are they? Total trips, total peaks, average peaks divided trip, total distance, and simulation duration, efficiency score. Optimization method is Hungarian algorithm, path planning, nearest I/O point. And yes, I'm continue, and we can look at our outputs. I passed that visualization part because the important thing is here optimization logic. Okay, and here let's start by looking at the summary you see at the very top of the screen, and you can see a single number telling you the total weighted travel distance after the assignment step. Think of that number as a quick score for how efficient the whole layout is. The lower it is, the better system is at placing high demand items closer to the I/O points. You can see how many storage locations we used, how many products we were assigned, and how many trips were generated for the pickers. So before we even go into the plots, this small section already tells you whether the algorithm did a decent job. Okay, let me alignment. So when you look at it closely, you notice blue circles marked as storage locations and the little green lines here running from each assigned product to one of the red stars here. Okay, and here red stars show which I/O point was chosen as the closest. You'll notice how many of the frequency products cluster near those I/O points. That is exactly what the assignment algorithm tries to do. At high frequency items create more walking time if they are far away, so placing them close pays off. And as you move your eyes across grid, the spacing stays uniform because we define the warehouse as structured rows. And what changes is which product shows up in each spot. And here's something students often wonder: why do some lines look thicker than others? For example, look at that area. That's because we scale the line width by different demand frequency. Higher demand means the line is a bit bolder, so you are getting an immediate visual hint about which products are more active without reading any numbers. And if you focus for a moment on the left side here, near IO1, you will notice clusters of lines converging there. Okay, that tells you how many products were assigned to that site due to either their distance or their demand. On the other hand, let me show you here, the far right region around IO2 hosts the assignments that made more sense for trips starting or ending on that site. And okay, picker trip analytics dashboard is here. Welcome. So what's happening here? The idea here is to understand workload patterns. The bar chart on the left shows how many trips each picker gets, and in this run all three pickers received exactly the same number of trips. That's helpful because it means we didn't overload anyone. Moving to the next chart, the distribution of peaks per trip, what you are seeing is that every trip ended up with the same number of picks. And that makes the picking workflow stable and predictable. The timeline chart here on the right shows when each picker starts each trip. And when you look at these dots, you can see that the activities are spread out over the whole simulated window. That spacing helps avoid blockages at the I/O points. If all pickers started at the same time every time, you would see those points bunching up. Yes. And next, take a look at the top picked products chart. This tells you which products got pulled more often during the simulation. It lines up well with the demand frequencies we assigned earlier, so the warehouse layout was not just optimized on paper, it actually leads to realistic picking behavior later in the simulation. And right next to it, there is a bar chart showing the travel distance for each picker. The values are close, showing balanced distribution. If one bar were way higher, it would tell us that the warehouse or the trip generation biased one picker more than the others. Okay, now look at that summary box. It lists the total number of trips, the total picks, the average picks per trip, and the total distance walked. When you see a total distance value, it comes from summing all the step-by-step distances each picker walked. And the efficiency score you see there is calculated by comparing the theoretical minimum distance to the actual distance walked. You won't see the formula here, but underneath the hood, it's simply what is that? Minimum distance divided by actual distance times 100. If the score is high, the picker movements are close to ideal. Okay, and snapshots here. Movement snapshots here. These 6 panels together show how the pickers move as time goes on. The first name starts at 0 minutes, as you can see here, where everyone is sitting at their initial I/O point, right? You can see them as colored circles and blue, and here a red star. Okay, and here once you jump to the second frame, the lines start appearing. Okay, these represent the trace left behind by pickers as they walk, and the faded segments near the beginning of each trial show older positions, while the darker segments show more recent ones. That fade effect comes from gradually increasing each line segment's transparency, and it helps you follow the motion without cluttering the whole screen. Now as the simulation reaches the halfway mark, you will notice more overlap. That's why path planning logic matters. Since each picker always heads to the closest I/O point and follows straight line movement between peaks, you end up with these angled segments connecting locations. Real warehouses often restrict movement to easily, so in a real-world model, those lines would not be straight. Okay, but for this simplified example, straight line routing gives you a clean view of which routes get more traffic. Another thing worth noticing is how each picker's color helps you isolate their path. When the screen gets busy, it becomes easier to identify who went where just by following each color. Okay, and the trials look like a mesh of crisscrossed lines because by then the pickers have completed several trips. The little arrows at the ends of the paths show the direction the picker is currently moving, and those arrows come from checking the last 2 points in the path and calculating the change in x and change y. and if that change is the arrow points in that direction. And you will also see the time label in the corner of each panel, right? Like that, that. And at the bottom, you'll see a quick list of insights we generated. Instead of thinking of them as conclusions, treat them as quick observations. They point out that the optimized layout lowers total walking distance, that the picking load averages out well across the 30 trips, and that traffic stays smooth with the chosen path method. And the layout influences the picking paths, the demand patterns influence how busy each location becomes, and the simulation helps diagnose where friction might appear. And thank you for listening.